Good. Welcome. So, that's part of the this IT conference thing, and I was asked by Mark to give a talk on something called computational seismology. So, I will briefly talk about what we do as a seismologist, and then talk about some IT issues related to that. Seismology mostly got two essential components, as some of you already know. The first one, the field installation of seismographs. So, pointer. Oops. How do you do that? Anyway, so don't need a pointer. Oh, this one. Yeah. So you can see here, this one actually where is it? Corey? Malawi, yes. It's Corey, it's here, and it's Yuchang. This one is in Botswana, right? So you can see we got a lot of publicity there. So what we do is we install something called a seismograph or seismic station. So you can see the station has several components. The first one, the solar panel, is provide the power, and this is the thing that frequently gets stolen. So you put this in somewhere in the wild. So sometimes people take it. It's good stuff in most part of the world. We have a GPS receiver. So this one actually tracks the time, and that's very important for us to mark every single recording data points, the exact time. Then we have recorder, so which is this thing here, this one, this situation. We have the hard disk, that's the old version of the seismograph. Then we put a sensor on the ground, so it's buried. Normally, the whole system costs about $30,000 to $40,000. So each of these. So that's how expensive it is. Okay, so we do a lot of travel. So I've been doing this since the early 1990s. So the Lake Baikal in Siberia, Russia. Actually, in 1991 I was there. That time they were called, the country was called the Soviet Union. Then next year become Russia. Right? So then this is the Ethiopia. So I put here, I paid a quarter for taking pictures with this camel, actually. This one is in Zambia. That's last year. So, in Kansas, 2000, Mozambique, different places. So we travel a lot. This is a sensor, so that's one type of the sensor. So this sensor itself costs about $20,000. So that's a very sensitive equipment. So how sensitive? If you have earthquake magnitude 5 or a little bit larger than 5 occur in China, this thing can sense that in gravity. So the waves travel all the way through the earth. Takes about 15-20 minutes to get here, but after come to here, this system can record the vibration of the ground. So part of the project, I travel a lot. Spent 9 months in the Siberia, Mongolia, sometime in South Africa, and central part of Africa, Ethiopia, different part of the world. So that's the fun part as a geophysicist. So as a result, we did a lot of publications on different parts of the world. So that's each thought I just put it as an article. Okay, so part of the project we are working on. We have several projects going on, but one of them we call the Safari. So that's a seismic arrays for African rift initiation. So it's more than $1 million grants to university. So actually that's part of a bigger project. It's about $5 million total. So it involves several institutions, MIT and Columbia University in New York, and the University of Texas and Oklahoma State, different universities. So this project actually, power project, as part of it, we put a lot of stations. So this one, 50 here. Several years ago, we put 18 there. So that's that's a network to study the rift system. Remember, there is a rift valley all the way from here to Kenya, to Tanzania, and all the way to Mozambique. So that's a very large system. So if this system continues in the future, this will be ocean. The ocean basin is developing. So I mean, all the oceans in the world come from this kind of rifts, right? So I mean, we can address a lot of questions using the data. So for example, why continental rift? What kind of the influence of early, the early structure can have, all these things. So actually, right now we just finished the installation of a local station. So here the Google Earth map, the station is somewhere here. So this computer science building, right? So if you go there, there is a structure there. So we spend like $20,000, $24,000 pay the physical facilities to build this system. So if we, in the near future, we'll put a sensor there. So the data will be recorded continuously. So when you walk there, be careful. You will be recorded, right? So the data will be shared by everybody in the world, actually. So that's real-time recording. So RADA will be one of the seismic stations. So that will be a very good facility for us. So we will name it MS&T1. So that's everybody know that's from MS&T, right? Okay, so what do we get? I mean, from all this hard work, we got these wiggles. This we call the seismograms. So in this case, each wiggle is recorded by one station. So that's 50 stations in Africa. You can see, the travel time actually different. It tells you a lot of things about what's going on beneath the earth, beneath the surface. Right? So the travel time is delayed in some area relative to other area. That means you get some slow, maybe hot melt material, and the waveform also different. So you can see the waveform sometimes like this, sometimes broader. So every single information here tells you a lot of things about what's going on beneath the earth. So that's the basic idea. So that's why computer is very useful. Okay? So this one shows you about 200,000 seismograms recorded by all these stations below, so across the country. So the National Science Foundation actually spending many millions of dollars now doing a project across the whole U.S. So each of this actually, each single line here is one seismogram, and this shows you something very interesting inside the Earth. So here's the depth here. So 410 kilometer, 670 kilometers. So you have this, change in the rock type from here to here. So we can see this very clearly. So using the data, using the information carried by the seismograms, we can study the structure of the Earth, the potential for earthquakes and volcanic eruption, and how and why do earthquakes happen, and the cause of large features such as why we have Rocky Mountain there, why we have a new magic seismic zone in Missouri, right? So why we have the volcanoes in the Oregon, for example. So all this information can be found in the seismograms, but also natural resource exploration. So these are very useful information. So then the second part is computational part. So as I said, there are two major components. One is the field components, another one is the computational part, right? So there are several topics. The first one is the spatial and temporal variation simple distribution of earthquakes. So you can see each dot here is an earthquake occurred in a in a 10-year period in California. So actually there are so many, 140,000 of them. So most of them you cannot feel. It's very small, right? But the seismic stations can record them. So what we did was actually very simple, count numbers, right? So we count number how many earthquake occur per day in that area. So it's a very simple, processing. Maybe the computer codes like that long, all you need, right? So you can see a very fancy feature. So after a certain time in 1992, you have this kind of annual cycle. You can see. So during springtime, you have a low number of earthquakes. During every year, during the fall, you got a lot more earthquakes in there. You have a decay feature. Right? So what caused that? So after a lot of thinking, we think it's caused by the pressure change in the air. So the pressure actually can change the earthquake occurrence. So because that's so unbelievable, we published in the journal Nature, right? So it's very difficult to make a publication there. So that's one of the things we do. So another one is very fancy is in 2001, a student of mine and myself published a paper about Japan. So Japan is here, so that's the northern part of Japan. And we found that in the Pacific Ocean, there was something very strange. There was a big change in something called a B value, or the frequency magnitude distribution earthquakes. So the idea that you have more small earthquakes than the big ones, so the slope is actually a straight line. So we found these two areas had a very big change before and after 1995, I think. So then 10 years later, there was a huge earthquake occurred. Start from here to all the way to here, all the way to there. So that we believe that time, we believe that it's caused by the coupling between the subduction, right? This one is subducting this way, so these two particles stuck to each other. So this one is not moving or moving slowly. So then accumulate force, right? So after some time, 10 years later, after this publication, a huge earthquake occurred. Remember, I think March 11th, right? 2011. So it caused damage to the nuclear power station, all the things. So this is an example of the studying the distribution of earthquakes. So another one called seismic tomography. So we know CAT scan, as some of you saw this before. So what is CAT scan? So it's not scan CAT. So it is a computer-aided tomography. So most of you are working, have been in the hospital, right? So you can see that's the patient here, and you have source. That's an X-ray source. And you got receivers here. That's a detector screen. So you can actually, without opening up people's body, you can see what's going on inside, right? So, and for our purpose, we use seismometers like this kind of things as the receiver. So on Earth, currently get maybe I think 50 to 100,000 of these kind of things, right? So then every time the earthquake, the waves travel through the Earth, travel through different parts, and get recorded by the sensors. So you can see, these are wiggles. So through these wiggles, we can see a lot of things about the Earth. So this is a result of CAT scan, right? So you can see the different structure there. And this is a result of seismic tomography. So you can see all these, low velocity structure here. It's a hot material coming up through beneath Africa and beneath the Pacific Ocean. So that tells you why in Africa is so high. So Africa is very stable, but the elevation is so high. So one of the reasons people think it's caused by this kind of hot material, pushing up, trying to get out of the surface. So that's one of the applications of scientific computing. So the next one we call residual function. The idea is also very simple. You have a conversion, a P to S conversion. Then, So you can actually stack the traces and do some kind of deconvolution, get something called residual function. Then you can do stacking. After that, you can see the distribution, I mean, how thick is the crust, or all this, why you have a thinning of the crust beneath the Lake Baikal, for example, right? And you can do a search for the best combination of the thickness of crust and the ratio between P and S3 velocities. So I mean, these are just some example of how useful the data could be. So we can measure the metal flow or metal fabrics. And for example, you have anisotropy, right? Anisotropy structure here, like this material is anisotropic. That means if you drill this way or that way, you stiffness strength, right? So it's seismic anisotropy because it's directional dependent. So in the Earth, you also have this kind of thing. So when wave travel one way, different velocity travel another way. So you can see, for example, you have a wave coming, and you can actually see the difference in the speed. So this actually is caused by the olivine. The olivine, that's kind of mineral, right? So more than 60% of the mantle of the Earth is olivine, like this. Remember, there is a movie called The Core, right? So some of you saw that, The Core. So something wrong with the core rotation, so that the magnetic field stopped. Some birds, cannot fly anymore. So then people drill a hole. I mean, actually, they drive a kind of a machine going down to the mantle, try to start the core rotation. Yes. So you see the green things. These are olivine. So that's the only thing can be right scientifically, actually, in that movie. So anyway, so in the mantle you have different mechanisms can form this line up. So our seismic the waves can detect this kind of line up. So that's called anisotropy, and this is a result for the whole U.S. I mean, central and western U.S. You can each of this little bar is actually a wave travel through the Earth. You can see the major features of we call mantle flow. The flow beneath in the mantle. So it's about 200 kilometers or something deep. You can see the very nice pattern of the flow. Actually, one of the students, several students published a paper with us, because we believe it's caused by this kind of mantle flow going around North America. Right? So that's one of the results of this kind of practice. Okay, so what kind of resource we need for computational seismology? So most of our tasks are data and CPU intensive, right? So that they are also long-running, so weeks or even months. So that's require IT to keep the computer running for a long time. So they are diverse in nature. That means we are not using one single software. So we write our own codes, and we use other people's codes. So that they are diverse. And also, we normally use a single Linux server. So do all the work. So at this stage, we have this one, the R43. SCAL is actually it's a Dell computer with 16 processors. So in the future, last year actually we wrote a proposal. So Dr. Liu and Andy Eckert and myself wrote a proposal to NSF. So we are requesting another Dell computer. So that's a 64 processors, 1 terabyte of RAM. So this one's 48 only. So this is 1 terabyte of RAM and 36 terabytes of disk space. So we were just told that they are going to give us money to buy it as long as NSF does not cut the budget. Right? So that's very likely. Maybe within a couple of months, we will have a new computer, which is much more powerful and a lot of space. So, as some of you know, for our jobs, actually, the bottleneck is not the CPU. It is the I/O speed. I just did a screenshot of this. You can see, people running things, and we only use 1%. For example, things like this, only 7% of CPU time, right? The reason for that is the data input output takes a lot of time, so that slows everything down. So another key is uptime. So most of the jobs have take a long time, and I just did the uptime this morning. So you see this machine been running for more than a year. So this is really good. It's very unusual, I believe. The reason for that is the IT research support team did a great job to maintain the thing, that computer. So 375 days have been running. So I mean, I will thank the IT people to support that, and we will continue to work with IT to do some good research. You have questions?